All right, everybody, welcome back. Today what we're going to do is we're going to work on what we call finite differences, which is going to help us determine what type of polynomial is present in a table. And then we're going to take a look at some regression models. So the first thing we normally start off with is a table much like this. And I would ask my students to go ahead and try to figure out what type of function this is. Now, most students would look at this and recognize, oh, wait a minute. The difference in my y values is adding 3 every time. So we look at it and say, well, I know that linear functions increase by the same amount every time. So therefore, since my first difference, the difference in the y values, the outputs, is the same, then this is going to be something with x to the first power or a linear function. All right, so that's typically the thought process that goes through our heads, and that's actually correct. Now, we've got new situations like this where usually the same thought process takes place, where what we'd have to do is we look at the difference. I'm subtracting 9, subtracting 5, subtracting 1, and then I am adding 3. Now, this is where most students stop. We say, okay, well, it's not linear. I don't really know how to go any further. But if you look at these values, you might notice another pattern. What's happening between these numbers, -9, -5, -1, and 3, is we are adding 4 every time. So the first difference was not the same. So that tells us that the equation, the polynomial, does not have a degree of 1. But the second difference was all the same, right? We've got 4, 4, and 4. So because the second difference was the same for all of our values, that tells us the degree of this function is going to be 2. Therefore, this is going to be a quadratic function. Now, there's going to be other things. We might be adding some other values, some other terms here. We might have a negative in front or a positive. It doesn't need to be 1, but we're not really concerned about what that is. The idea here is we can use what we call finite differences to determine what type of polynomial function is represented in a table. All we have to do is check the difference between our outputs. Then if those are not a consistent number, check the difference between those values and those values and those values and those values. And our process would continue until we get the correct answer, or hopefully a number that we are going to have in common. What I would like you to do is pause the video, write this down, and then try to see if you can determine what type of polynomial that this table is, the polynomial that's represented in this table. I'll give you a second to pause, and then I will do this on my own. All right, so we're doing the same idea. I'm going to check to see if it's linear first. We are adding 18, adding 6, but then I add 0 and 0. And that doesn't really work for me, right? Those are all not consistent numbers. So therefore, the first difference is not constant. These values, right, are not constant. So it is not a linear function. All right, so let's check the difference in those values. We have -12, -6, plus 0. Again, it is not our second difference being constant, so therefore the degree is not 2. It is not a quadratic. We can do this one more time, and we can see we are adding 6 and adding 6, and therefore this is a constant number. So our third difference was a constant, and therefore the degree of the polynomial that's represented in this table is going to be 3, and therefore it is a cubic function. This is how finite differences work. You take a look at the difference, and once the value becomes constant, that tells you what type of polynomial this is going to be. Now, this is great and all, but usually the next step is for us to write an equation. I don't know about you guys, but we're not entirely confident yet on how we can write the equation of a cubic function in this example based on these points alone. Now, if we had x-intercepts, then maybe, but we don't have just x-intercepts, so it's not really going to work very well for us. I want to jump back to here, and you'll see why in a second. If I wanted to come up with the equation for this, what I can do is I can create what we call a regression model. A regression model is basically using our calculators to determine the best possible equation to fit this data set. All right, and so there are two ways we can do this. I'll kind of show you both ways, but primarily we use Desmos, and I feel like that's the easiest for us to do, so that's what we're going to use. So what I did is I went ahead and I plotted these values in Desmos. Now, you can kind of see that this could look like a quadratic, but it's not super clear. Maybe it is a cubic function that snakes through there, and we just don't have enough values. We're not entirely sure. Well, what we can do is we can tell our calculator, in this case Desmos, to come up with an equation that fits the data as best as possible. Now, that equation is going to be our regression equation. So we have y1 because the values in our table have a y1 value. If you look at the top next to that green circle, it says y1. If it was a y2, we put y2 and so on and so forth. All right, then I'm going to use the tilde. That is a squiggly line there. All right, and then I'm basically going to write a quadratic equation. I have a as my unknown leading coefficient, x1 squared, plus b x1 plus c. Now, sometimes we have a difficult time remembering where this might come from. If you take a look at this, this is really just a regular quadratic in standard form. We have a coefficient, our x to the second power, our b value, which is another coefficient, times x to the first power, and then another coefficient times x to the 0. A, B, and C are just consistent, and you'll see why we might want to do that a little bit later on, but you can really use whichever values you would like. Now, in this table here, they give you A, B, and C values. What that is saying is, hey, if you want to write an equation, it would be of the form, and again, we know this is quadratic because that's the regression equation we put in, y equals that A value, x squared, plus the B value times x plus the C value. This is the equation that will allow us to go through each of the points in this table. And if we go back here, you can see the red graph on the side goes through all of those points. Now, what really tells us is we have this r squared value here. The r squared value is very important. The closer it is to 1 means it is a better fit. Well, 1 is exactly 1. So this tells us this is exactly a perfect fit. It is perfect. So that's how we know that this is in fact a quadratic, which actually confirms what we did before with our finite differences. All right, so other functions, if we wanted to do cubics, I would change my first exponent to a 3. Then my second exponent would be a 2. Then c would be x1 to the first, and then we would need to add a d value. Again, we could see this in red. Let's see if this is fitting for us. Sorry, I'm clicking some unnecessary buttons here. And we should have a cubic model here, but we can't really see that from the graph. So I'm wondering if I might just have to retype this back in here. So I'm going to go back home and I'm going to type in y1, that squiggly line, which is a tilde, a x1 to the third, plus a b x1 to the second, plus a c x1 plus d. Now, I've got what looks like a quadratic, but technically this is the cubic equation here, right? A x1 to the third plus b x1 to the second plus c x1 to the first plus d, which is x to the 0. Now, the a value here would just be 0, and all that's telling us is that really a quadratic is the best fit. All right, but the important part for us is by adding terms, going from a quadratic to a cubic to a quartic, then a 5th degree, 6th degree, 7th degree, what we're doing is we're allowing the equation we want our calculator to come up with to have more opportunities to turn, which means it's going to fit the data better and better as long as we keep adding terms. So a cubic is going to fit just as well as a quartic, and so on and so forth. Now, that's not exactly true, and the reason that this is because these values perfectly represent a quadratic. And that's what we can see having an a value of 0 here. But I really just wanted to show you that if it was a cubic, this is what it would look like. If I wanted to do a quartic value, I would again make this one to the 4th power, then bx1 to the 3rd, then cx1 to the 2nd, then d would need an x1 plus, I would use e, but e is actually a mathematical number, so I'm going to use f. And again, it gives me the equation that would match if I wanted a quartic function. So this is a quartic regression. Really, the pattern kind of continues from here. In Desmos, if I want to create a linear function regression model, I do y1 because those are the y values in my table, a tilde, a x1 because the x1s are the x values in our table, plus b. Okay, well, quadratic's going to follow the same idea, but it's going to be a quadratic in standard form. So it's x1 squared plus bx1 plus c. A cubic would follow the same idea, and we basically just keep adding letters on and increasing the degree. y1 tilde ax1 to the 3rd plus bx1 squared plus cx1 plus d, and so on and so forth. So this is how easy it is to come up with a regression model on Desmos. Now, if you wanted to use your calculator, you're welcome to do that. What you can do is press stat and then 1 for edit. That will allow you to enter some values into your list, and that's what I did. I entered my table values here. Looks like I'm missing a 4, so I just put that 4 in. Now, what I'm going to do is I'm going to press stat again, and I am going to press calculate, or calc at the top. Now I can choose what type of regression I want to make. Now, I use finite differences to determine that this was a quadratic. So if I click on quadratic, I don't need to put anything for those values, but I press enter, and it will give me some numbers that should match this. Now, this didn't work out perfectly, and you know what? The actual reason for that is, if I go back to my list, this is actually the cubic list. So let me do that. Let me calculate a cubic regression from here. If I do that, again, I get an r squared value of 1, which tells me it's a perfect fit. And then I know my coefficients a, b, c, and d there, which gives me my necessary equation. So I can go back over here. My regression model for my calculator told me it is y equals, let me double check what those are, 1, -3, 2, 1, x to the 3rd, -3x squared, plus 4x, let me double check that, 2x plus 4. So this is the regression model for the table right there. All right, it is really that easy. Now, there's a little bit of a different approach we can get to when we look at real data. As we know, real data is not perfect. All right, when you are collecting data, it doesn't always perfectly follow a pattern. And so what that means is we can't actually use finite differences always with real data, because real data is rarely ever perfect. It rarely ever fits into a perfect pattern, a perfect equation, and everything is nice, neat, and orderly. Let's take a look at an example. So it says the table below shows the numbers y of moose on Isle Royales in Michigan during year T, where T equals 0 corresponds to 2010. Find a model for the data. Use a model to predict the number of moose in 2025. Now, this table of values has T values as X's, but the idea is still going to work the same way. T is the number of years since 2010. So when T is 0 here, that represents the year 2010, 2011, 12, 13, 14, 15, 16, and so on. So this is basically telling me that in 2010, there's 150 moose. In 2011, there's 515, so on and so forth. We're going to collect this data, and I want to try to come up with a regression model so I can make predictions. That's the importance of regression models. Now, I'm going to try to use finite differences. And I'm going to show you that it doesn't always work with real data. So if I take a look at some of these values, the difference between these two is 365. The difference between these two is 235, then 225, then 75, then 200, then 50, then 300. So this is my first difference. My first difference was not a constant, so it tells me that the degree of the polynomial that best fits this data is not going to be linear, at least for now. Now, I'm going to pause this real quick and I'm going to fill in the rest of the values. I'm going to keep going. I'm going to find the difference between these values and the difference between those and those and those and those. I'm going to pause it to save us a little bit of time. All right, so I did all the work here, and as you can see, I checked the first difference, which told me it wasn't constant, so it's not linear. Then I checked the second, the third, the fourth, the fifth, and the sixth, and then I kind of ran out of values, because after this, I would only have one number, and I wouldn't be able to tell if it was constant with all the other values that I was given. And the reason that this is because real data is not perfect. The regression equation will not perfectly fit all of the data points, always when we're dealing with real data. So what we're going to want to do is we are going to use our regression model. So I'm going to erase all this just so we don't need to deal with it anymore. And now what I'm going to do is I am going to use this to enter all of my data into Desmos. So I'm going to erase these tables, and then I'm going to create a new one, and I'm going to fill in. So again, I'm going to pause the video, fill in the tables, and we'll go from there. All right, so I put in all of our data. If I click on the little magnifying glass, it shows me my values. I can't really tell what type of function this is going to be. It kind of has an upward curve there, but it could be linear. It could be part of a real big quadratic. It could be part of a real big cubic. I'm not really sure. So what I'm going to do is I'm going to type in regression equations one at a time. y1 tilde a x1 plus b. And it gives me some values there. All right, remember, I am trying to look at that r squared value. The closer it is to 1, the better fit it is going to be. Now, if you look at this, 0.96 is pretty close, which makes sense because the green line fits the data pretty well. Now, it doesn't go through all of our values, so it's not perfect. That's why all of our coefficients there, the a and the b, are not whole numbers, and it's not going to work out that well for us because, again, real data is a little bit messy. So now I'm going to create a quadratic regression. y1 tilde a x1 plus, I should square that, plus b x1 plus c. Those are my values. And again, as you can see, the r squared value is starting to get a little bit closer. So I'm going to keep going. I'm going to try a cubic function. Let's do y1 tilde a x1 to the third plus a b x1 squared plus c x1 plus d. And again, the r squared value is a little bit closer. So what this tells us is our values, our polynomial equations, are going to be getting closer and closer and closer. And this goes back to what I said earlier. 0.99 is pretty darn close. All right, it's a really, really good fit. Now, if I keep adding terms, so I added a term to go from a quadratic to a cubic. If I wanted to go to a quartic, then a fifth degree, and sixth degree, seventh degree, I'm giving my polynomial more opportunities to turn, so more opportunities to fit through the data. What that means is the r squared value should just keep getting closer and closer and closer and closer to 1. All right, so at some point, we need to kind of decide which polynomial regression equation we are going to use. That is when we typically, at least in my class, we tell our students, hey, calculate a cubic regression in this case. So we've got our cubic values there, and it tells us our coefficients. So I'm going to jump back to these notes. And what that means is I can come up with my equation, y equals, and I'm going to take the a value I was given, which is about 6.31, x to the third, plus my b value, which is actually a minus 78.6, 0.55 approximately, x squared, plus my c value, which is 445.75x, plus my d value, which is about 144.55. This is the regression equation I would use depending on what your teacher tells you to create. Again, this is my cubic regression. So again, in a problem like this, I would usually tell my students, hey, create a cubic regression model to represent this situation. And again, because if I just keep adding terms, then it's going to keep getting closer and closer, and it will just continue to improve always. All right, so this is the equation that I am going to use. The second part of this says, use the model to predict the number of moose on the island in 2025. Well, 2025 is how many years from 2010? Well, the answer is 25. So what I want to do is I want to use this equation I just created and predict what happens when my input, and I changed it to an x, is going to be 25. So I'm going to use this equation, and in place of all of my x values, I'm going to plug in 25 instead. And I can do this on a calculator to go ahead and simplify my work. Let me capture this real quick so we don't waste any more time. I'm going to get rid of some of these. And I'm going to type in, you know what? I might want to keep these. I'm going to get rid of my extra ones. So I'm going to do 6.31 times 25 to the third minus 78.55 times 25 squared plus 445.75 times 25 plus 144.55. My answer is 788.3. 60,788.3. Now we're predicting how many moose we are going to see. We can't have a decimal for a moose, so I am actually just going to round up and say that this model we created is predicting that we are going to see 60,789 moose in the year 2025 in the given location. So that is the beauty of regression models. What we're doing is we're taking data and finding an equation that fits it as best as possible, and then we're using it to make an estimation. And that's basically what it is, okay? So this is how regression models work. We talked about finite differences here, which you can only do when the data is perfect. So usually we tell our students when to calculate the finite difference and use it to determine the degree of their polynomial. And then we've got regression models, which allows us to take data points and essentially plot them and come up with equations that match the data as best as possible. All right, so the key part is really remembering what to do in your calculators, and that's kind of this part here. You create tables, and then you need to determine which of these, and there are others as well that we didn't discuss, is going to give us the best equation. Okay? If you have any questions or concerns, please feel free to leave a comment. Thank you for joining today, and enjoy the rest of your evening.